When I made the video saying, that I was done with Anton, I said, oh, maybe I'll count theorems. Now that I'm about to start on FIS, which is, of course, Friedberg, Insel, Spence, I want to do a count. I actually did do a count of all the theorems that I attempted. So, of course, Anton's here just as a prop because I'm not going to open the book. And so is FIS. It's only a prop. It's already got the little thing that I do for the exercises where I don't look at them and I only look at the answers. So it's ready to go to get started with. But then in this video, really, all I'm going to do is go through the notebooks quickly. I hope it's not too long of a video. I did the count, and the total count is, it's all these added up, chapter by chapter. And I've got, let me see the number, 207. And so I attempted 207 different proofs in reading Anton. So I've got markers for the sections. Hopefully I didn't screw up and mark a section as theorems that I attempted when in reality is part of a section. And I'll show you how easy I can make that mistake. But I think I only highlighted clusters of theorems that I attempted versus theorems that were part of the reading. Because I was really only counting my little squares that I use for when a theorem is done in the notes. Oh, never mind. That's just problems. Yeah. So for example, if I always use this little square to say, okay, QED, the theorem is done. But this is part of the reading. This is just the book. So these little notes, these little things that I put, these markers, I'm going to keep them there because as I go through FIS, I'm going to always want to go back and say, okay, how am I doing, and which theorems did I already prove to my satisfaction. The system that I use is if I put a diagonal lines on a square, I feel confident that I got that right. Now remember, I tried many even problems for which there were no answers. So whatever is here is what there is as far as I'm concerned. And if I leave it empty, if I don't do the diagonal lines, it means that I don't feel confident that I did it correctly. Also, sometimes I'll have like 2 pages that I tried for a proof, and I know for a fact I didn't even get close to proving that. I don't even have that. I just write move on. And I'm not counting those in the 200. Yeah, that's it. Okay, so here goes. So in this case, this is section 1.3. If AB and BA are both defined, then AB and BA are square matrices, right? And yeah, I'm just going to read a few. I'm not going to read all 200. And of course, my counting is a little different from the number of problems in the book. If there was a section A, B, C, and each one was a separate proof, I count each one as a proof because I did each one as a separate proof. Yeah, so some of them, like for example, if A is invertible and K is any non-zero scalar, then K times A, the matrix, all of it to the n is equal to the scalar K to the n times A to the n separately, n being an integer. Yeah, and I feel like I proved it correctly. Then, see, here I felt that I got very close, and I did have an answer in the book. It's an odd number. If this matrix is an elementary matrix, then at least one of A, B, C must be 0. Yeah, I looked it up in the answer, and I got close. Then, and of course there are clusters. Some sections have a lot of theorems that were requested to prove. 31. Now, in some cases, even the odd number, I had to click the tripod. Sorry about that. In some cases, even though it is odd, there is no answer in the answer book. So if there's no marking right next to it, it means that this might as well be an even problem. So here is 31, which goes, if A and B are m by n matrices, m rows, n columns, then A and B are row equivalent if and only if, this is a little symbol that I use for if and only if, A and B have the same reduced row echelon form. Yeah, so I went through and I wrote out what I thought was a correct proof. Then 32, if A is an invertible matrix and B is row equivalent to A, then B is also invertible. Yeah. Then here, there's yet another cluster of theorems that I attempted. Let the matrix A times the vector x equal the 0 vector be a homogeneous system of n linear equations in n unknowns that has only the trivial solution. If k is a positive integer, then the system a to the k times the x vector is equal to the 0 vector also has the trivial solution. I feel like I did it correctly. And it doesn't have an answer in the book because I didn't make a marking of it. Then there are additional proofs. I'm not going to read every single one. I'm just going to highlight a few of them because, of course, we've got a lot of them. Okay. So here's one where I chose to just write it out with the matrix and multiply it out. Sometimes in the book, Anton is, of course, more clever, obviously, a lot more experienced. And sometimes he would just use index notation for his proofs. In my case, I'm a noob. I just wanted to write them all out. So if A is a symmetric n by m matrix and B is any n by m matrix, then the following products are symmetric. B transpose times B, B times B transpose AB. Of course, now we know that this is similar to a similarity transformation, even though it isn't. But yeah. So I worked it out in detail, and then eventually I just wrote it out clean. Yeah, I wrote it out clean. And we're still in chapter 1, but I'll go faster because there's a lot to cover for all the theorems. But I just want to highlight a point that I want to make, that there are a lot of theorems in Anton, and I attempted a chunk of them, a good count of them. Every square matrix A can be expressed as the sum of a symmetric matrix and a skew-symmetric matrix. And I'm already 6 minutes into the video, 7 minutes into the video, so I'm going to just skip along. I just wanted to read a few. I think if I read them all, I will make too long of a video, which is not my style. So here you have more problems and more proofs in section 2.1, and with a nice little square of like I feel like I did it right. Determinant proofs, additional proofs. Yeah. Then on to, yeah, and these are problems, yeah. An even problem in section 2.3. A square matrix A is invertible if and only if ATA is invertible. ATA comes out again later on with SVD. So now I know. Additional proofs. Okay, so that is the first notebook. And I'm going to go a little faster for the other ones because I just want to make one video. I just want to highlight that sure enough, there are a ton of proofs in, I'm sorry, I was going to leave this in. I don't want to take it out. Okay, so this one, 24, is u plus v is equal to u plus v separate, if and only if one of the vectors is a scalar multiple of the other. Yeah, and it is a problem, and it is a problem in chapter 3. And as I showed before, the problems with lots of the chapters with lots of proofs are 1, 2, 3, 4, 5, 6, and 8, but not 7. 7 and 9, I didn't do any, even though I think there may have been at least one proof. Yeah, I think so. So, and then of course the ones with the most are chapter 1, 4 vector spaces as expected. Sure. See, so then, of course, chapter 4 with all the vector space axioms, that makes for a whole bunch of proofs. Sort of like an easy source of proofs problems. Then here we have for 43, I'm sorry, section 4.3. Oh yeah, we've got a couple of proofs in here. Yeah. And I'm not going to read them all, just highlighting that there's a whole bunch of them. R to the infinite, the infinite R real space is an infinite dimensional vector space. Then we go through a lot of material that had not that many proofs, more calculations, and then here we go. If a matrix A is not square, then either the row vectors or the column vectors of A are linearly dependent. And that was notebook number 3. I mean number 2. Then off to number 3. Don't want to spend too much time beyond what I had allotted for this exercise. The characteristic equation is that. Prove it. Do the determinant. Then here you've got a similarity transformation proof that, see, so in some cases, even though I did some, I was like, this is not good enough. I'm not going to even put a square on it. This one, I do not feel confident that I did it correctly. This whole thing about rank and nullity equals the number of columns, and proving nullity and rank by itself as similarities proved a little hard. I definitely want to make a mental note. I want to come back to this with FIS. If A is diagonalizable, then so is a to the k for every positive integer k. Yeah, so we're in the similarity transformations business. More vector mechanics. Yeah, norms, inner product spaces, theorems that were requested. Did a whole bunch of them. But I hope FIS has more, or the same with more explanations, and then I can get some of the ones that I got wrong, or I feel like I got wrong, right. If V and, yeah, so here's another inner product. I'm not going to read it, just going to keep going. Then here we have another proof. U and V are vectors in an inner product space. A, the norm of U is equal to the number of V if and only if U plus V, U minus V is equal to 0. Yeah. And then do a geometric X interpretation. Then here we go for if X, the vector X is an n by 1 matrix, then the matrix A is equal to this expression. And I think I got it right. Took me a while, actually. There's no showing in here how much I worked on this problem. Okay, and I think we're near the end of this notebook for what I wanted to show. More mechanics of vectors. And then the last notebook has only a little more because chapter 8 did not have as many theorems. So a transformation theorem, another one. Yeah, more linear transformation theorems. So that's it. So yes, I did attempt a whole bunch of theorems in Anton, but FIS, I hope, will either help me to clean up the ones that I got wrong or to give me some new ones. I know that there are new ones because it's direct sums and direct products and dual spaces in FIS.